All right, so we'll take another problem here. Number 37, calculate the percentage yield in the photosynthesis reaction by which carbon dioxide is converted to sugar. So here's the reaction. CO2 plus water yields this C6H12O6, which is called glucose sugar. If 7.03 grams of carbon dioxide, so we have 7.03 grams of carbon dioxide yields 3.92 grams of sugar. And so this means that there must be excess water present. So they only give us one of the reactants. So we'll assume the other's in excess. Or, it doesn't have to be in excess, it could be stoichiometric as well. But it's not limiting. And so this must be limiting. And so 7.03 grams of CO2, what would we do first here? Is this the actual yield or the theoretical yield here? This is the actual yield. So the first thing we have to do is calculate the theoretical yield. And so how would we calculate the theoretical yield? We go from grams of CO2 to moles of CO2, moles of CO2 to moles of sugar, moles of sugar to grams of sugar. So let's see how many grams that comes out to here. And so this is what they did. So grams of CO2 to moles of CO2, moles of CO2 to moles of sugar. Here it's a 1 to 6 mole ratio, so it doesn't always have to be 1 to 1, 1 to 6. And then moles of sugar to grams of sugar. And so the theoretical yield is 4.80, the actual yield is 3.92. And so they got 3.92 grams out of a possible 4.80, so times 100%, which gives us an 81.7% yield. That's pretty good. Okay, so those are calculations for determining percent yields. And then how do we use it? We use percent yields in two ways. And so let's take a look at the first way we use it. The first way we use it is based on how much product we get. And so let's look at this one. Calcium cyanamide is a common fertilizer. So this when mixed with water in the soil, it reacts to produce calcium carbonate and ammonium. And so this is calcium cyanamide. It's very interesting because of the CN2. The CN2 anion you didn't have to memorize, but it's a CN2 with a -1. This is not two cyanides, it's one cyanamide. And so this reacts with water. This is a Lewis acid-base type reaction. This Lewis acid-base reaction is going to produce calcium carbonate and ammonia. The ammonia is what's going to fertilize the soil.
So calcium cyanide, is that toxic?
Calcium cyanide is toxic, but calcium cyanamide is probably a lot less toxic. It's a cyanide ion. Okay, how much ammonia can be obtained from 7.25 grams of calcium cyanamide in a laboratory experiment in which the percentage yield? So they're estimating the percentage yield to be 92.8%. So they're going to lose. How much are they going to lose? They're anticipating of losing.
7.2.
Yeah, 7.2%. They're going to lose. And so what they're asking here is, okay, how much can they expect to recover based on losing this much, or retaining that much? And so what do we do here? Well, this is going to be dimensional analysis in which we're going to use the percent yield to figure out how much product we end up with. And so doing that, we'll start off with 7.25 grams of calcium cyanamide, CaCN2. And then where are we going to go? We're going to go from grams to moles. So calcium is what? 132.91. 132.91. Carbon is 1201, and then two nitrogens. Nitrogen is 1401, so this is going to be 2802.
Professor, calcium is 40.078.
Oops. Calcium's 40 point, what is it?
078. 40.078.
078, so we'll go 40.08. Round it up. All right, thanks for doing that. So this is going to be 11, 10, 80, 11. And so we're going to have 80.11 grams per mole. CaC and 2 cancels. And then we go from moles of calcium cyanamide to, what are we after here? Ammonia. So we're going to go from moles of calcium cyanamide to moles of ammonia. What's the mole ratio here? There's 2 moles of ammonia produced for every 1 mole of calcium cyanamide. Yeah. So now we have moles of ammonia. And then from moles of ammonia, we're going to go to grams of ammonia. And so nitrogen is 1401, and then 3 hydrogens is going to be 303, so 1704. So this is going to be 17.04 grams of ammonia per mole of ammonia. Okay, if I stop here, what do I call this? If I stop here, I call this the theoretical yield. So up to this point, I've just calculated the theoretical yield. But am I going to get the theoretical yield? No, because you know what? I'm expecting losses. Now, how much loss am I expecting for the product? Yeah, and so what that means is I'm only going to recover a certain amount. Now, how much am I going to recover? And so this is going to be 92.8 grams of actual yield for every 100 grams of theoretical yield. And so up to this point, so for this many, I'm not going to get all 100 out of 100. I'm only going to get 92.8 out of that. So let's calculate this. So I'm going to stop at the theoretical yield first. So this is going to be 7.25 divided by 80.11 times 2 times 1704. So in theory, I should, the theoretical yield is going to be 3.084 grams of ammonia. And so in theory, that's how much I'm getting, but I'm going to lose. I'm going to lose 7.2%. And so I'm going to do times 92.8 divided by 100. And so in actuality, I'm only going to get 2.862 grams of ammonia. This is my actual yield. And so in theory, I'm going to make this much. In actuality, I'm going to get this much. And so this is using the percent yield to figure out how much product I'm actually going to get. The other way we use this is differently. So here, when I look at this, next question here is HCl and iron. This is a single replacement reaction. What will the actual yield? Okay, so 3.17 grams of iron. So we're going to react 3.17 grams of iron. We're going to figure out the actual yield of iron 2 chloride. Well, actually, we don't have to figure. Yeah, the actual yield based on losing. In this case, we're going to lose a lot more. And so we'll calculate the theoretical yield and then cut it down to get the actual yield. So this is the same problem we did before. However, if you look at this next problem is different. The Haber process for making ammonia from nitrogen in the air is given by the equation. So we take the nitrogen, react with hydrogen to make ammonia. This is an example of a element plus element combination reaction, or redox. It's a redox reaction. Calculate the mass of hydrogen that must be supplied. Okay, so what they're doing is this. Calculate the mass of hydrogen that must be supplied to make. So this is the actual yield. So they're giving us the actual yield here. That's how much we want to make. And so what they want us to do is they want us to figure out how much hydrogen do we have to start with. And so in other words, this is like the cookie example. In the cookie example, we had a targeted actual yield. And so we have to figure out how much reactant we need for that targeted actual yield. And so at number 35, we're given the actual yield. So this is going to be 5.00 times 10 squared kilograms of ammonia. This is our actual yield. So if we want that, then in theory, we have to make more because of losses. Now, how much more do we have to make because of losses? Well, it depends on this. And so what does this 88.8% yield? 88.8% means 88.8
Survive.
actual, yes, survives out of 100. So only 88.8 survive out of 100. These are the survivors here. And so what that means is we need to multiply this by 100 divided by 88.8. And so this is going to be, for every 100, only 88.8 make it through. And so, well, this is going to be kilograms. It doesn't matter. Kilograms here. So 88.8 kilograms of ammonia. This is what we call the actual yield of ammonia for every 100 kilograms of ammonia that we produce in theory. And so here we can get rid of the kilograms of ammonia actual yield and replace it with kilograms of ammonia theoretical yield. So we're going to have to make more, because we're going to lose some. All right, so we go from kilograms of ammonia probably to grams of ammonia. And so I'll just do 1,000 grams per kilogram here. And then from grams of ammonia to moles of ammonia. So it's 17.04 grams of ammonia per mole. And then they wanted to know how much hydrogen we need to start with. And so there's 3 moles of hydrogen for every 1 mole of ammonia. And then we're going to figure out how many grams, or actually kilograms, since we're dealing with kilograms here. So hydrogen, I'm going to use 108 now, so this is going to give me 2.016 grams of H2. I use 108 rather than 101 to get 4 sig figs per mole of H2. And then we'll convert it to kilograms, 1,000 grams per kilogram. And so I have to start off with extra, and this is just the calculation to see what that extra amount is. And so the 1,000 divided by 1,000, thousands cancel. So I'll go ahead and do the calculation. It's going to be 500 times 100 divided by 88.8 divided by 1704 times 3 times 2.016. 199.84. 199.8 kilograms of hydrogen. Now, if I didn't have this loss here, then I wouldn't need as much hydrogen. If I didn't have this, let's say 100 out of 100 made it through. If 100 out of 100 made it through, let me go ahead and times this by 88. Actually, 0.888. Oh shoot, I lost it. 199.8. 199.8 times 0.888. 177. If I didn't have this loss here, then I would only need 177.4 kilograms of hydrogen. But since I have that loss and I'm anticipating that loss, I'm going to have to start off with more. So I'm going to lose. Does that make sense? So it's a 177.4 kilograms of hydrogen if 100% yield. It's going to be 199.8 kilograms of hydrogen with 88.8% yield. So let's check the answer there. They rounded it. Did they round it? I don't know. Unless I did I do calculation error?
They didn't do the grams.
No, they just left it in kilograms, which is okay. They did kilimoles.
That was the 2 moles of ammonia.
Oh, that's where I screwed it up. Here. I made a mistake here. I did 3 moles of hydrogen per 1 mole of ammonia, and it's actually per 2 moles of ammonia. So I have to divide my number by 2. And so 199.8 divided by 2, 199.8 divided by 2, 99.9. This comes out to 99.9 kilograms of nitrogen. Or what they got, 100 kilograms. This number is going to be off to 99.9. Times 0.888. 88.7. 88.7. Sorry about that. 88.7. So we are going to have to use about 100 kilograms here. We'd only have to use about 89 kilograms. If it was 100%. Okay, is that clear? So there are 3 things we're going to do. 1, we're just going to determine the percent yield. 2, we're going to figure out how much product. And 3, we're going to figure out how much reaction.
What does that calculation do then to get 88%?
Oh, I just took out this. I redid the calculation without this, or I just changed this to 100 over 100 and redid the calculation. So I just removed this term.
Oh, because I don't want 100%.
Yeah, or if it's 100% yield, then it's 100 out of 100, so it's just 1. And so redo the calculation without it, basically. All right, any questions on this? We're almost done with this chapter. There's pretty much one section left in this chapter. I skipped this comparison of moles. I don't like that method, 10-5. So you could skip 10-5 as well. You could use either, unless you like it. I mean, if you're familiar with this, go ahead and use this. But I completely skipped this. So we have just energy and the thermochemical equations and thermochemical stoichiometry left to do. So endothermic reactions require energy, exothermic reactions release energy. So we can figure out how much energy is required and how much energy is released depending on reaction. Now the first thing for energy are the units of energy. These are the units here. We have a calorie. The calorie is abbreviated CAL. There are actually 2 calories. There's a lowercase c and an uppercase c. For food, we use the uppercase c. For chemical reactions and whatnot, we use lowercase c. And the food calorie is 1,000 chemical calories. And so let's say you have a 1,000 calorie meal. A 1,000 calorie meal, well, what that means in terms of chemical calories is 1,000,000, which is like 1,000,000 would be like 1,000,000 calories. Which isn't, so you just had a 1,000,000 calorie meal, but nobody wants a 1,000,000 calorie meal. So we use a big C for that to cut it down. Well, a calorie is defined as the energy required to raise 1 gram of water by 1 degree C. So that's how much energy. So if you took 1 gram of water, which is a milliliter, and increased the temperature by degree C, it would require 1 calorie of energy. We don't use calories that much. We use joules a lot more. Joules defined a little differently. Joules is defined as mechanical. Rather than heating something up, it's mechanical work. So if you took a 1 kilogram mass and lifted it up by 1 meter against gravity, that would require a joule of energy. What's a joule? Both the calorie and joules are small amounts of energy, so typically we use kilojoules and kilocalories instead. And so 1 kcal is equivalent to 1 food calorie, which is equivalent to 4.184 kilojoules. But we do that conversion later. Okay, this is the capital C. So the capital C calorie is used when talking about food energy, and it's actually the kilocalorie. Typical diet provides about 2,000 calories per day, or 2,000 kcals. the lowercase c. Food calories, 1,000 thermochemical calories. A U.S. federal law, the Nutrition Labeling and Education Act, requires that most food packages display nutritional information. And so the first thing is doing these unit conversion. So we'll do typical conversions would be, you know, for me, like kilojoules to kilocalories. You know, even though they give you additional conversion factors, I only remember one. And the one I remember is 1 calorie is equivalent to 4.184 joules. That's it. And so I don't like this kilomole type stuff that they did in the last problem. You know, kilomole. That kind of stuff. I just prefer just to convert it. And so let's take a look at this particular problem. Consider the kilojoule to kcal conversion first. Analyze the sub-problem listed and want to identify, change the equivalency to the needed conversion factor. So your book loves to do this. This is the conversion factor that they're going to come up with. 1 kcal is equivalent to 4.184 kJ, but I don't bother doing that. And so let's take a look at the problem. This is the practice exercise 10, 12. A 1 ounce serving of almonds is 1.6 times 10 squared, capital C, food calories. Express this in joules and kilojoules. So this is the only conversion factor I remember here. Oh, actually one more because we need the food calorie. So 1.6 times 10 squared, capital C calories. And so what I do is I get this to lowercase c calories, and that is there's going to be 1,000 little cals for every 1 big cal. And so the food calories cancel, that leaves me with the thermochemical calorie. And then I'll go to joules, 4.184 joules per calorie. That takes me to joules. So we want to go to joules and kilojoules. And so here, let's just click the answer, save some time. We're going to get 6.7 times 10 squared. 6.7 times 10 squared is about 670. Actually, I'm going to do the calculation. I don't like the rounding here, so we'll go 160 times 1,000 times 4.184. That's because, do you see what they're doing here? Anyway, I get 669,440 joules. How many joules? And so to round this, this would be 6.7 times 10 to the 1, 2, 3, 4, 5. 10 to the 5th joules. Okay, to go from joules to kilojoules, we just move the decimal. So if we're going to a bigger dimension, we're going to go to a smaller number. So this would be 669.4 kilojoules. Or to round it to the correct number of sig figs, it would be 670 kilojoules. So that's what they got. They wrote it. Or 6.7 times 10 squared kilojoules. The reason I like to do it this way is I always have the same core. You know, I always go back to the same conversion, and then I just try to find my way to there, rather than having a whole bunch of different conversion factors memorized, which is a pain. So some reactions are exothermic, some are endothermic, and these are two examples of reactions here. This one is exothermic because you see delta H is the amount of energy released in this as heat. H stands for something called enthalpy. So this whole term we call heat of reaction. If the heat of reaction is negative like this, it means that this reaction is going to release 2,855 kilojoules when we burn 2 moles of methane along with 7 moles of oxygen to form 4 moles of CO2 and 6 moles of water. We're going to get that much energy. Now, if we change the amounts here, we're going to get different amounts of energy. So, for example, if we only burn 1 mole of methane rather than 2 moles of methane, so if we burn 1 mole of methane and excess oxygen, we're going to get half as much energy. If we burn 3 moles of methane, we're going to get 3 times as much as burning 1 mole of methane, or ethane, sorry. So that's the amount of energy that's released. Well, the amount of energy that's released is as a product, and so this is why they put it as a product here. There's no such thing as negative energy in thermodynamics. So, for example, energy is like money, and the sign is just to tell you the direction. So if you lost, let's say your bank account went minus $20, does that mean you just deposited a minus $20 bill? No. It means that you lost positive $20 out of your balance. And so this is the same situation here. There's no such thing as minus 2,855 kilojoules of energy. That minus just means that, well, this reaction just lost it. And so the reaction went from here down to here, and that was 2,855 kilojoules.
So if the energy was positive, the energy would be on the other side of the equation?
Yes. If the energy is positive, it would be on the other side of the equation. It would be endothermic. So we'll just see that here. This is an endothermic reaction here. You see here the energy is on the other side, and so we write it as positive here. It's going to consume, so it just increases by 92 kilojoules versus decreasing. And so we're out of time, so we'll use these numbers. I guess I'm not quite finished. Almost finished. We'll do some stoichiometry problems with this. So.